Okay, so hello and welcome back. So in this video we want to do start from exercise number 9, and exercise number 9 is consider. So this is exercise number 9. We have consider f as a function from R plus, meaning non-negative real numbers, meaning that all the positive real numbers including 0 to basically the set -5 to infinity, given by f of x is equal to 9 times x squared plus 6x minus 5. I want to show that f is invertible with f inverse of y is equal to the square root of y plus 6 minus 1 over 3. So now in order to solve this problem, so I have tried, you wouldn't get anywhere if you try to prove that f is 1 1 and onto, meaning that if you try to prove that f is 1 1, you would get into trouble. Now suppose that I want to show that, for example, I want to show that f is 1 1. So in order to show that, I have to show that for every x1 y x2, f of x1 is equal to f of x2. F of x1 is equal to f of x2 implies that x1 is equal to x2. Now it might actually work, but the last time that I tried this, I didn't get actually anywhere with this. So actually I might have tried a different method. Let's see if it works this time. So f of x1, basically you know that f of x is equal to 9x squared plus 6x minus 5, and f of x1 based on this would be 9x1 squared plus 6x1 minus 5, and f of x2 would be equal to 9 times x2 squared plus 6 times x2 minus 5. And now if I think that we can actually do this. So if I write, so what I can do is that I can take f of x1, if I call this 1 and if I call this 2, I can take 1 and write it as 9 times x1 squared plus 6 times x1 minus 5. I can write it as 3 times x1 whole squared. So 3 times x1 squared, and then I want to make it a perfect square, okay? And so I write this as 3 times x1 whole squared plus 2 times 3 times x1, meaning that basically you have basically a plus b. A plus b whole squared is the same thing as a squared plus 2 times a times b plus b squared. So from this side of this expression or this equation, I want to create I want to create this that you can see over here. So out of basically 9x1 squared, I write basically 3 times x1 whole squared, which is and so now basically 3 times x1 becomes a, and so that becomes a squared, and then I need a 2 over here, so I put my 2 over here, and I have to multiply it by a 1 by a, which happens to be 3 times x1, and now if I do the multiplication here, I'll get 6 times x1, which is all that I have here. I don't want to change this, so I take my b, which is what has to be multiplied by this expression. I take my b as simply 1. And now if I multiply all of these things, I'll get 6 times x1. This is basically what I was looking for. So this is a squared plus 2ab. That means that my b now has become 1. So I write a 1 squared. And now this is a squared plus 2ab plus b squared. Now, of course, this expression is different from the expression that I have here. There is some difference over here in the constant over here, meaning that here I have a 1 and here I have -5. So I have to subtract a 6 from here, and now 1 minus 6 is equal to -5, and now everything is okay, except that this part is actually a squared plus 2ab plus b squared, right? Which I can write as a squared plus 2ab plus b squared. I can write as a plus b whole squared, which means that this is equal to 3 times x1 a plus b, which is equal to 1, b which is equal to 1 whole squared. So that means that, so this is basically now this expression over here. And there is a -6 over here, and that is basically 1. Now I need to do the same thing with 2, meaning that I write 2 as 9 times x2 squared plus 6 times x2 minus 5. And as you can see, the coefficients and everything are the same, only the variables are different. So then I can write this as 3x2 plus 1 whole squared. I'm writing this based on what we did here, minus 6. Now if I say that f of x1 is equal to f of x2, what that means is that this is f of x1, right? So I can write this as 3 times x1 plus 1 whole squared minus 6 is equal to, and this is f of x2, which is 3 times x2 plus 1 whole squared minus 6. Then I can simplify these two, and then I can take the square root of both sides of this equation, meaning that I can write the square root of 3 times x1 plus 1 whole squared is equal to the square root of basically 3 times x2 plus 1 whole squared. And now you can see that over here what we are saying is that x belongs to this set that is only 0 and basically positive numbers, which means that if x is a 0 or a positive number multiplied by 3 is a positive number, plus 1 becomes a positive number, and so if I take the square root of the square of that expression, that gives me only a positive number, meaning that you can imagine that you have, for example, you know that, for example, -3 squared is equal to 9, and also 3 squared is equal to 9. Now if I want to take the square root of 9, which is the same thing as the square root of -3 squared, which is the same thing as the square root of 3 squared, I have to basically account for I have to account for the negative numbers that could have been multiplied together to give 9, or positive numbers that could have been multiplied together to get 9, and so I get positive or negative 3. That means that the square root of 9 is not just positive 3, but it's plus or minus 3. Now, if I know if I know beforehand that basically that the number that I multiplied together was a 3, and I write 3 times 3 is equal to 9, then, which is equal to 3 squared, then if I calculate the square root of 9, which is equal to the square root of 3 squared, that is going to give me only 3, because I know that basically this is the number that I started with, and this was a positive number. So I'm doing the same thing over here. I am doing the same thing over here, meaning that in order to take the square root of this, of the square of this expression, I need to know if this expression was positive, negative, or basically what this expression was in the first place. Sometimes it's not possible to know, so in those cases, when you have, for example, the square root of 3x1 plus 1 all squared, and when you want to take the square root of that, you have to write it as plus or minus 3x1 plus 1. There is no other way to do it. I mean, if you don't know, if there is no limitations on x, then you have to write it this way. But if you happen to know that, for example, here my x, which is basically a subset of this set, or belongs to this set R plus, then I know that my x is a positive number, or a 0. It cannot be a negative number, because my domain is the non-negative real numbers. And so a non-negative real number, when you multiply it by 3, that's still a non-negative real number. Add a 1 to that, that's still a non-negative real number. And so based on that, I can write this as 3x1 plus 1 is equal to 3x2 plus 1. And then I can simplify these two and divide by 3 both sides. I'll get x1 is equal to x2. Which proves that basically over here we said that f of x1 is equal to f of x2. And then here that implies that x1 is equal to x2, which means that f is 1, 1, or injective. Now another way to do the same thing is using a graph. Another way of doing the same thing is the graph, although that's not a very reliable way of doing that. Meaning that on a graph, first of all, you might not be able to see the whole domain of the function, because your graph goes from, your function goes normally from, for example, it's a large domain. I mean, it goes from negative infinity to infinity, or basically all of the positive numbers, all of the negative numbers. But still you would get some idea about whether the function is 1, 1 or not. So if you want to do that, if you want to just take a look, and that's no proof, and you shouldn't actually accept it, except for functions that are very limited in domain. In those cases, then you know basically what's going on. It's not specific to for this function. I wouldn't recommend this for this function. But if you graph this function here, for example, if you go for basically 9 times x squared plus 6x minus 5, you can see that your function is basically a function like this. and I do not have any reason to believe that this function is going to be doing anything else except for what it is doing here. So you can see that it's a parabola. Of course, it's a second degree equation, so it's going to be a parabola. And you see that there is a minimum here, which is at x at y is equal to -6, and then from there the function is basically, it has two legs, and then the function is increasing and increasing and increasing from both sides, which means that there is no way that the function can be and now there is a problem here. No, actually there is a problem here, as you can see. So for example, the output of this function is for this x, for x is equal to whatever this x is. For example, for this x, 0.483, the output is 0. For another x, -1.15, the output is again 0. That means that this function is actually many 1, right? This is not a 1-1 function. But we have limited the domain to all of the x's greater than or equal to 0, which means that the function practically starts from this point 0, -5 and just keeps going, increasing forever, right? Which means that then the problem of being many 1 doesn't really ever arise. And so now, based on the graph, you can clearly see that your function is 1-1, of course, provided that you put this restriction on the domain of the function, meaning that, of course, if the restriction wasn't there, then of course the function would be many 1. It's like some function, like for example f of x is equal to x squared. It's not many 1. At x is equal to 1, your output is 1. At x is equal to -1, again your output is 1. So the function is not 1-1. But again, when you limit the domain, you have no problem. So that's another way of knowing whether the function is 1-1 or not. Now, once you have made sure that the function is 1-1, then you need to make sure that the function is onto or surjective. Now, in order to show that, basically to show that f is onto, of course, onto from the domain to the codomain of the function, right? To show that f is onto, or basically surjective, what you need to do is that you need to show that every output of the function, or every member of the codomain of the function is the image of some element in the domain of the function. And for that, we usually find the inverse of the function, and then use that relationship between x and y in order to decide whether for every y that we can find in the codomain of the function, there is an x that has been mapped to that. And then if that's the case, then you can make sure that every element in the codomain is an image, and so there your problem is solved. Okay, so now in order to show that f is onto, let's take a look at our function. Our function is basically 9x squared plus 6x minus 5. 9x squared plus 6x minus 5. 9x x squared plus 6x minus 5, and that is f of x. Now you can argue that basically you can set, for example, you can argue that let y be a member of, or be any member really. Let y be any member of the codomain of f. That is basically let y belong to basically this set over here, which is -5 to infinity. -5 to infinity. So if that is the case, and of course we know that y is equal to 9x squared plus 6x minus 5, right? And let y be equal to 9x squared plus 6x minus 5. Now if that is the case, then I can write basically now you see that now basically, in order to find basically what this equation is giving me, it's giving me every y. Now this is, for example, this is the codomain of your function, which is basically all of these elements from -5 to infinity. -5 to infinity. And this is the domain of your function, which is R plus. And this is f that goes from this set to this set, right? Now, you know that when we say that let y be any member of the codomain of the function, that is, y belongs to this set, that means that here you have your y's. And any y that you can find here, well, as far as we are hoping, as far as we are concerned, we know that every y that we can find here basically is equal to, we can get to that y through this rule on the domain of the function, meaning that whatever element you have over here, you have to put it into this equation, into this expression, and as x, and then calculate, for example, f of 1, f of 2, f of 3, and so on and so forth, until you get to the corresponding element in the codomain of the function. Now, if basically, at this point in time, I do not really know if every element that I can find here, if it's possible for me to get to every element in this set using this rule, meaning that it's possible that, for example, I have this set over here, this is my domain, and this is my, for example, this is my codomain, and this is the rule on the function, let's call it f, and there is all of these elements over here, and there is all of these elements over here as well, and this element is mapped to this element under f. All of these elements are mapped this way, but there is one element in here that it has not been mapped to, which means that there is no way to get to this element through this rule on the domain of the function. And so what that would mean is that basically then in that case, for example, f is not onto, or is not surjective. Now, so this process is just simply a process of making sure that the range of your function, which is basically all of these elements that are the images of the images of some element in the domain of the function, that this set, which is the range of your function, is the same as the codomain of your function, meaning that every element in the codomain of the function is the image of some element in the domain of the function, right? So so now what I'm going to do is that now this basically this relationship between x and y that we have here, this relationship gives me any y that, provided that y has been mapped to from x, not the y's that might be loose over there, not the image of some element in the domain, but only the y's that have been mapped to in the codomain. This y gives me some relationship between those y's and the x's that we have used in order to get to that y, right? Now I want to use this equation in order to make sure that, in order to check really whether every y is it the case that every y has been mapped to in this set, or is it some select number of y's that have been mapped to and there are some other y's that are not the images of some element in the domain of the function, right? So, and for the same reason, now this gives me y in terms of x, meaning that it tells me for every y, basically it tells me for every x what y I can get to. Now if I want to know for every y what x I can get to, meaning that the reverse process of that, I have to find, now you can see over here that we have found y in terms of x. So then the reverse process would be finding x in terms of y, which is basically the process of finding the inverse of the function. Or simply you can say that you want to calculate x in terms of y. Now the problem here is that your x's are, one of them is raised to the second power, one of them is raised to the first power. They are not together, so we'll have to find a way in order to put these x's together before we can express y, before we can express x in terms of y. And the only way that as far as I know, the only way that there is to do that is, or at least the only usual basic way that there is in algebra to do that, is that you have to make a perfect square out of the right hand side of this expression, and take the square root of that perfect square, so that x comes out and then it becomes only one term, which means that basically I will write my x as I will write this as a perfect square. Now you know that basically a plus b whole squared is the same thing as a squared plus 2 times ab plus b squared, which means that basically if I can express this, the right hand side of this equation, as the right hand side of this equation, then there is a chance that I can write the expression as a plus b whole squared. So now let's try to do that. So I write y is equal to, basically instead of 9x squared, I want to write this as a squared. So instead of 9x squared, I write it as 3 times x whole squared. And so now my a becomes 3x. And so I need a 2 over here, I need my a over here, which is 3x, and 2 times 3x is equal to 6x. So since I don't want to change this equation as much as I can, I just simply put a 1 over here, multiply this by a 1, so that I don't change this expression or this term of the polynomial. And then now my b becomes 1, so I have to write the b squared over here as well, so that is 1 squared. Now this expression is this equation has a negative 5 over here. This has a 1 over here. That means that I have to subtract a 6 from here in order to basically in order to have the exact same polynomial down here. So 6 minus 1 is equal to negative 6 plus 1 is equal to negative 5, and the rest is really the same. So now this part is the same thing as a squared plus 2 times ab plus b squared, which can be written as a plus b whole squared, right? So then I can write y is equal to basically a plus b whole squared would be 3x plus 1 whole squared, and there is a negative 6 over here as well, which means that basically if I take the 6 to the other side, y plus 6 is equal to 3x plus 1 whole squared. Now my goal was to get to x, and still I have to do something in order to get to x. Now if I take the square root of both sides of this equation, what I will get is that the square root of 3x plus 1 whole squared, and since x is a non-negative real number, then 3x plus 1 is also a non-negative real number, it's a positive number. So then the square root of 3x plus 1 whole squared becomes simply 3x plus 1. And this becomes, well, the same thing, the square root of y plus 6. And again, in order to get to x, I write this as 3x is equal to the square root of y plus 6 minus 1, taking 1 to the other side. And so x is equal to basically the square root of y plus 6 minus 1 divided by 3. Now this is the same equation that we had up here. This equation was y in terms of x. This equation is x in terms of y. That means that now any x that I have in the domain of the function, now I know how to now I know basically how for any y how to get to some x. That's basically what it does for me. Okay, so now what we need to do is that we need to make sure that basically we need to make sure that every element that we have in here, we need to make sure that every element that we have in here in the codomain of f is the image of some element in the domain of the function. So the range of, or the codomain of f is negative 5 to infinity. Is negative 5 to infinity. That is basically the codomain of basically f. And what I want to do is that I want to make sure that all of these elements get through to I want to make sure that all of these elements are images of some element in the domain of the function. So how do I do that? And the way that I can make sure that is the case is to use this equation, because this is basically the inverse process of the function that we had in the first place. So the function was f of x is equal to 9x squared plus 6x minus 5. In this function, basically, I enter x and it gives me some image of x in the codomain of the function. Now we have made some changes to this, and as a result, we have gotten this equation. Now this equation tells me for every y what I'm going to get as an x, right? And using this, I want to make sure that all of these elements can actually be and will actually be mapped to from some element from the domain of the function. So that means that these elements must be, of course, these are your y's, and they must be permitted or allowed to be entered into this equation as y. Now the condition that we have here on y is that, of course, since y minus 6 is the argument of a square root function, then y plus 6 has to be greater than or equal to 0, meaning that y has to be greater than or equal to negative 6. So since y is greater than or equal to negative 6, and here we are talking about y's negative 5 to infinity, so then all of these y's are actually allowed to be input here. You have no problem with that. But then again, you need to make sure that for all such y's, there exists an x that can actually map to them. That's also important. Meaning that sometimes, for example, you get this equation x in terms of y, and of course your y, you can enter it here, and you have no problem with that. But then there has to be some x in the domain of the function that can actually map to that element y in the codomain of the function. Otherwise, the whole thing doesn't make any sense. So now what that means is that if I suppose that so over here y's greater than or equal to negative 6 are permitted here. Now suppose that I enter exactly negative 6 into this equation as y. Then x would be equal to basically the square root of negative 6 plus 6 is equal to 0. The square root of 0 is equal to 0. So that's negative 1/3. Now negative 1/3, x is equal to negative 1/3. Now over here, what we said was that f goes from r plus to basically this set. That means that your x's can come only from this set. And this set is the set of non-negative real numbers, meaning that negatives are just not there. Meaning that this x, as you can see here, this x actually does not exist in your x's. Meaning that then this element y is equal to negative 6 cannot even, well, you can enter it into the equation, there is no problem with that, but there is no x for that, right? So for the same reason, you need to consider all of these things. Now I do not really need y is equal to negative 6, that's not my problem. My problem is that all of y's starting from negative 5 all the way up to infinity, belonging to the set of real numbers, that has to be permitted or allowed to be entered into this equation. And for all such y's, there has to exist some x in such a way that that x basically maps to that y, right? So now I start from basically y is equal to negative 5. So if y is equal to negative 5, over here x becomes, if y is equal to negative 5, then x becomes basically the square root of negative 5 plus 6 minus 1 over 3, which gives me basically the square root of of 6 minus 1 is equal to 1 minus 1 is equal to 0, so this becomes a 0. So that means that when y is equal to negative 5, then x is equal to 0. And x is equal to 0 actually does exist here, because this set does include 0 as well. And as I make my y's greater, meaning that, for example, suppose that I go for y is equal to negative 4, then x is going to be equal to the square root of negative 4 plus 6, for example, minus 1 divided by 3, which is equal to the square root of 2 minus 1 over 3, which is something about, for example, something above 0, right? It's a positive value above 0, because the square root of 2 is equal to 1 point SQRT of 2 is something about 1.4, and 1.4 minus 1 is equal to 0.4, 0.4, and 0.4 divided by 3 is equal to 0.13. So that exists again in this set. Again, 0.3 exists in this set, and then as I make my my y's greater and greater, meaning that going from -5 to -4 to -3 to -2 to 0 and so on and so forth, x's get greater and greater, larger and larger, and so we have no problem with the function. That means that the function is actually onto, right? So so then basically, based on this whole discussion, and this is something to be understood properly, otherwise otherwise you cannot work with these functions, really. Now and so you can say that therefore for every y greater than or equal to 5, there exists an x such that f of x is equal to y, such that f of x is equal to y. Hence f is onto. Now basically we showed that f was injective and also onto, meaning that it is surjective, meaning that f is bijective, meaning that the inverse of f actually does exist, right? So now let's calculate the inverse of f. Now to calculate the inverse of f, basically we had basically f was a function from R plus to the set -5 to infinity, -5 to infinity, and we said that f of x is equal to 9x squared plus 6x minus 5, 9x squared plus 6x minus 5, and we also found that f is bijective. F is bijective, right? We also found that f is bijective, meaning that the inverse of f exists. So now in the algebra that we did before, what we found was that x, basically based on this equation, we found that x is equal to the square root of the square root of y plus 6 minus 1 over 3. That was basically what we did before. Now what we can do is that to find the inverse of f, basically you can set let g, for example, or let f inverse let f inverse be the inverse of okay, so now we can say that let f inverse be the inverse of f, f inverse being a function as basically as f inverse from, it has to be from the from basically this set back to this set, right? So you can say that -5 to infinity all the way to basically r plus as, and I can basically I can define f inverse of y as this function as the square root of y plus 6 minus 1 over 3, because this function, as you saw, let us basically get back to every element in the domain. So that's going to be the inverse function that we can define. And so what that means is that basically f inverse of y is equal to this, from this domain to this codomain. And now what we need to show, in order to make sure that f inverse is actually the inverse of f, we need to show that, so basically now we said that f inverse of y is equal to this function down here. Make a screenshot so that so we said that f inverse of y is equal to the square root of y plus 6 minus 1 divided by 3, and f inverse we are going to define it as -5 to infinity to basically to r plus. And we said that f inverse, we defined f inverse as the inverse of f. Now, in order to show that f inverse is the inverse of f, we need to show that basically we need to show that f inverse composed with f is equal to I of x, and f composed with f inverse is equal to I of y, meaning that the inverse of the function composed with the function itself is equal to the identity function on the domain of basically f, and the function itself, the original function composed with the inverse of the function is equal to the identity function on the codomain of f, basically. So I know that, so basically we know that f is the same thing as f is a function from r plus to -5, infinity, and f of x is equal to 9x squared plus 6x minus 5 plus 6x minus 5. So Now if I calculate F inverse OF, what I will have is that is basically F inverse of f of x. F inverse of f of x is equal to, this is F inverse, so wherever you see the variable you have to replace it with the function f of x. With the function f of x, and the function f of x is basically this thing over here. So I have to write this as the square root of 9x squared plus 6x minus 5 plus 6 minus 1 divided by 3, which is the same thing as now you have over here basically the square root of 9x squared plus 6x, 6 minus 5 is equal to 1 minus 1 divided by 3. And so what we have here is basically 9x squared plus 6x plus 1, which you can write as 3x plus 1 whole squared, right? So I can write this as the square root of 3x plus 1 whole squared minus 1 divided by 3. And well, since basically 3x plus 1 is a positive value, then of course you can write this as the square root of 3x plus 1 whole squared is the same thing as basically 3x plus 1. And you have a negative 1 over here, you have a 3 over here, these two will be cancelled out, these two will cancel out, and this is equal to x. That means that F inverse OF is basically a function that gives you, for every input x, it gives you an input x, which means that basically F inverse OF is equal to I of x, or the identity function on the domain of f. And also we need to show that FOF inverse is equal to I of y. So FOF inverse is the same thing as F inverse of y. Now what that means is that wherever in function f, wherever you see the variable, you have to replace it with the function f inverse of y. The function f is basically this function over here. The function f is this function over here, right? So I write this as and the function f inverse is basically this function over here. So I write it down here so that we can see it. So if we said that f inverse of y is equal to basically the square root of y plus 6 minus 1 divided by 3. So that means that I can write this as 9 times, for example, that means that I can write this as 9 times x squared, which is basically f inverse of y. Now f inverse of y is this function. So you have the square root of y plus 6 minus 1 whole squared divided by 3 squared, and then you have plus 6x plus 6 times x, which becomes 6 times basically this function. So the square root of y plus 6 minus 1 divided by 3 minus 5. Now that is equal to 9 and 3 squared, you can cancel out. And this is the same thing as this is the same thing as a minus b whole squared. So you know that a minus b whole squared is equal to a squared plus or minus 2ab plus b squared. So this becomes basically y is you need to know whether y is you want to raise y to the basically you want to raise this to the second power, meaning you have to write basically the square root of y plus 6 whole squared and negative 2 times the square root of y plus 6 times b, which is equal to 1, and b squared is equal to 1 squared, and then you have 6 divided by 3 is equal to 2, right? So 2 times plus 2 times the square root of y plus 6 minus 2 minus 5. So that's the same thing as so this is negative 2 times the square root of y plus 6 plus 2 times y plus square root of y plus 6, and that is equal to, so you can cancel these two out, and now over here what you have is so you have a 1 squared over here, negative 2, negative 5, and this expression over here. Now in order to, so this is going to be equal to, of course, y plus 6, and this is going to be equal to 1, and this is going to be equal to negative 2 and negative 5. So negative 2, negative 5 is equal to negative 7, and 6 plus 1 is equal to 7, so all of them you can cancel out and you will be left with y. That means that this function, if you enter any y into it, it will give you y back. That means that f inverse is the same thing as I of y, meaning that and of course these two y's are different, as of course as you can imagine. This y is basically some y belonging to the codomain of the function, which is capital Y, and this capital Y is basically the codomain of the function, right? So you need to, of course, understand these things. It's not possible for me to denote my y's as lowercase and uppercase y's because well, it's just not possible in writing. It's not possible to distinguish between lowercase y and uppercase y. That's actually a problem. But I wish there was a way to do that. So that means that f inverse is equal to I of y, and now we have shown that f inverse of is equal to I of x, f inverse is equal to I of y. And that basically means that f inverse is the inverse of f. So that's basically what we wanted to show here. That was question number 9. Now in the next video we will talk about question number 10. I'll see you in the next video.